Okay, today we're going to be doing the normal approximation of the binomial distribution. So, when we looked at the binomial distribution, it was using discrete variables. So the binomial uses discrete variables and the normal distribution uses continuous variables. However, it was found that if the number of trials in a binomial distribution is really high, it begins to approximate the normal distribution. So let's think about the kind of problems that we would face with a binomial distribution. So say we had, we wanted to find the probability of obtaining exactly 60 heads with 100 tosses of a coin. And so we've got our number of trials n is 100, and a success is a head, and we want 60 heads, and the probability of a success is 0.5, and that's going to be raised to the power 60, and then 0.5 is the probability of a fail, and we raise that to the power of 100 minus 60, which is 40, and that would give us the probability. However, what if we wanted the probability of x being greater than 60, so having more than 60 heads? For previously finding out how to do that, we would have to go the probability. We've got the probability. We would have found the probability of 61, of 62, of 60 individually, then add up all these probabilities. That's a lot of work, and it'll take a lot of time. We can approximate the binomial distribution with the normal distribution. And we can then use our phi tables to then work out what that probability would be. So let's look at. So we're going to do some shapes of 4 binomial distributions for n equal 25. So 25 trials. So the first one looks like this. And for this one, n number of trials times the probability of a success is equal to 3.75, and n times q, the probability of a fail, is 21.25. Now we're going to look at the situation where n is still 25, but np is this time 8.75 and nq is 16.25. Ignore my dodgy lines, they're not very great. And you're starting to see normal curve kind of take shape here. Now we're going to look at the situation when NP is 18.75 and NQ is 6.25. And again, we've got something that looks quite like a normal curve. And finally, we're going to look at NP equals 23.75 and NQ equals 1.25. And this doesn't look like a normal curve. So what we can see is when NP and NQ are small, we don't have a good approximation to the normal curve. But look here, when we have NP and NQ quite large, it fits quite nicely to the normal curve. And in fact, the rule is if Z is a binomial distribution with n trials and probability p, it can be approximated by a normal distribution where with mu and sigma squared, so mean and variance, where the mean is equal to NP and the variance is equal to NPQ, provided that n is large so it's large enough so that NP is greater than 5 and NQ is also greater than 5. And that's what we see here. These two middle examples, both NP and NQ, are both greater than 5, but here NP is less than 5 and NQ is less than 5, and so we don't get the normal distribution. So this is a really important condition, and this is a really important rule, but it has to satisfy this condition here. Now, we need to bear in mind something else. So as I previously said, a binomial distribution is a discrete variable and a normal distribution is a continuous variable. So we need to then take into account the difference of the types of variables. So we need to add in what's called a continuity correction. So say we have a discrete variable x equals 13. It must be treated as being represented by a class of continuous values. So we need to think of x. So x is between 7.5 and 13.5. So if you think about it, this is the discrete variable, but if it was a continuous variable, it could take any value between equal to 12.5 or less than 13.5. So therefore we must replace our x equals 13 by either x equals 12.5 or x equals 13.5. And this here is what we call the continuity correction. But how do we decide if it's 12.5 or 13.5? So let's think about how we would do that. So let's think of an example where we wish to find the probability of x less than 13. But x doesn't include, so x, I'll make that a bit neater. X equals 13 is not included. So we use x is equal to 12.5. If we had to find the probability of x less than or equal to 13, so x equals 13 is included. Don't know what I've written there. We use x is equal to 13.5. Now we're going to do an example where we will explore the continuity correction in a wee bit more detail. So, given that x is a binomial distribution where n is 100 and p is 0.4, use a suitable approximation and continuity correction to find a p, the probability when x is less than 43 and the probability when x is greater than 43. So, firstly, let's think about what is the mean. If we're going to use, if we're going to approximate this as a normal distribution, so that's NP, which is 100 times 0.4, which is going to be 40. And variance is NPQ, which is going to be 100 times 0.4. Now Q is going to be 0.6, which comes out at 24. So we now know, because this is 40 and NQ would be 100 times 0.6, which is 60, They're both much greater than 5, so we can use the normal distribution. So we're going to use x is approximated to a normal distribution where the mean's 40, variance is 24. Now we need to think about our continuity correction. So let's think about if we had the probability density, and there's x, and we have, so here's our value for 43. Here's our value for 42, and here's our value for 44. And in the middle, we've obviously got 42.5, and we've got 43.5. Now, we want x less than 43, so not including 43. So we've got 42.5 is less than or equal to x is less than equal to less than 43.5. So that's the range of values that x would take if we're dealing with it like a continuous variable. Now we know for this one it doesn't equal 43, so the probability that x would be less than 43, we use 42.5. If probability of x was less than or equal to 43, we'd use 43.5, but this is the one we want because it doesn't include 43. For the other side of the problem, the probability that x is greater than 43, we'd use 43.5 because it doesn't include 43. But if we had the probability of x greater than or equal to 43, we'd use 42.5 because it's including 43, the value could be 42.5 and then rounded up to 43. But that's just, we're just explaining this for completeness, but in this example, it's greater than, so we use this value. Okay, so let's now look at the probability that x is less than 43. So we need to find, so our value for x is going to be 42.5. We decided that there. So our z value for the normal distribution will be 42.5 minus 40 over root 24, which gives us 0.5103. So this probability is going to be approximated to the probability that z is less than 0.5103, and so that's equal to our phi function, which we read off our table and is 0.6950. So that's the value of our probability. Now for the probability of x greater than 43, we're going to be doing the probability of z. So this time z is going to be 43.5 minus 40 over 24, which comes out at 0.7144. So z is greater than 0.4714. And for that, we know that that's going to be 1 minus the phi function, for 0.714, which comes out at 0.2377. And we can just round that up to 0.238. Okay, let's do another one. Boxes are packed with 8,000 randomly selected items. It is known that 0.2% of the items are yellow. So using a suitable approximation, find the probability that a box contains fewer than 20 yellow items, and b exactly 2 out of 3 randomly selected boxes contain fewer than 20 yellow items. Okay, so this is a binomial distribution where we've got 8,000 is our value for n, and our probability is 0.002. This is that divided by 100. So if we were going to change this to a normal distribution, our NP would be 16 NP, and our NQ would be 7,986. So definitely, they're both greater than 5, we can use the normal distribution. Our mu is NP, which is 16, and our sigma squared is NPQ, which is working out would be 15.968. So we're going to have a normal distribution with 16 and 15.968. Now we want the probability that their x is less than 20. So thinking about our continuity correction, let's think what x could be. X could be equal, oh dear me, what am I writing? X could be between 19.5 and equal to 19.5 or less than 20.5. Now because it's not equal to 20, x is going to be 19.5. So we can then work out our value for z. So it's going to be 19.5 minus 16 over our sigma squared, which is 15.986, the square root of that. And that gives us a value of 0.87587. So now we've got, this is going to be approximated to the probability of z less than 0.87587, which is the sigma, the phi function of 0.876. Reading that off the table, you'd get 0.8, oh, it's a terrible 0.94. So that's the probability that a box contains fewer than 20 items. Now let's think about part B. So we're looking that exactly 2 out of 3 randomly selected boxes contain fewer than 20 yellow items. So this is one of these boxes. So we're able to, so if we let y be the number of boxes containing fewer than 20 yellow items, then y is going to be a binomial distribution where we've got 3, the n's 3, and we have a probability of a success of 0.8094. So now we can work out the probability that y equals 2 is going to be 3, choose 2. Our probability of a success is 0.8094 squared times 0.1906 to the power 1, and that equals 0.375. Let's do one more. A fair coin is tossed 888 times. Find by suitable approximation the probability that the coin lands on heads at most 450 times. So X is a binomial distribution where n's 800 and the probability of success is 0.5. Our NP would be this times this would be 444, and NQ is also 444. Now this is going to be our mu, and sigma squared will be NPQ, which will be 222. So we can then do a normal distribution with mu 444 and sigma squared 222. Now let's think about our value of x. Now we were looking at the probability that x is less than or equal, because it has to be at most 450 times. So 450 is included. So x is going to be taking the value of 450.5, so the upper limit. So our value of z will be 450.5 minus 444 over 222, the square root of 222, which comes out to 0.4 0.36. So the probability is going to be approximated to the probability when z is less than or equal to 0.436, which equals the phi function of 0.436, which comes out at 0.6686, which we can round up to 0.669. So the probability that you get at most 400, its heads at most 450 times is 0.669. So I hope that all makes sense.